Hello and welcome to section 7.7. Today's section 7.7 is going to be covering alkene nomenclature and stability. And the reason why we're learning how to name alkenes and learn about some of their stability properties is because we learned how to make them in the last section, 7.6, which regarded the elimination reactions, E1 and E2. We need to know how to name these alkenes because we're going to start making them in reactions. And we also need to know how their stability, their intrinsic properties, might compare to one another for future reaction education. Now, the question is, how do we name alkenes? Well, first, we follow the IUPAC rules to start with. And those IUPAC rules, if you remember from Chapter 4 and earlier sections, are to identify the longest parent chain or ring, identify substituents that are on the longest parent chain or ring, to arrange them alphabetically after you do the numbering of those substituents. And remember, the numbering needs to be as low as possible, and the alphabetical arrangement needs to consider only the name of the substituent and not the indication of how many there are, such as mono or di, tri, tetra, and penta. You leave those off whenever you're arranging them alphabetically. With alkenes, however, there is an extra step at the end because this is a new type of functional group. And the extra steps are the parent is now going to end in "ene", not "ane". So, for instance, these two molecules on the left in black is cyclopentane. It's pentane because it is all carbon-carbon bonds with two hydrogens. However, the one in red is called cyclopentene because it has an alkene. Now, this is an example of how the naming changes based on the fact that there's an alkene involved. Also, sometimes we have to be able to number the alkene in case there are more than one ways that the alkene can be present in a molecule, such as like this one. This is a 5-carbon parent chain with no substituents on it to make it easier for us. And what we need to know, the second important rule for alkene naming, is that we also need to prioritize naming where the double bond starts by giving it the lowest number. It's important to note that it is where the double bond starts. So in this case, this molecule would be named 2-pentene or pent-2-ene instead of 3-pentene. The alkene must be named for the carbon at the lowest number that the alkene starts. So that's why we call this 2-pentene and not 3-pentene. And one special thing about alkenes in regards to how we name them is that they can have multiple degrees of substitution. And what I mean by that is that the patterns of substitution look a little different than they did for regular alkanes, in that you can have up to 4 unique substituents on an alkene group. And if you have between 1 and 4, we have special names for those through mono, di, tri, and tetra substituted. As you see here, mono meaning 1, di meaning 2, tri meaning 3, and 4 meaning tetra substituted. Remember, the R groups here represent just in general any type of group we can imagine, and they only serve as a placeholder so that we can better understand the overall pattern of substitution here. So now that we've talked a little bit about the nomenclature of alkenes, let's talk about the stability of these things. And mainly when we say stability, what we mean is we're going to be talking about how the stability changes between cis, meaning on the same side, or as we knew them before from our stereoisomer chapter, Z, how the stability of these molecules compares to E-alkenes or trans alkenes. And we call them trans because they're on different sides of this, this kind of imaginary parallel line that we draw right through the double bond. So you see that the trans is opposite that parallel line and the cis is on the same side. So there will be cases in the future where we need to think about which molecule might be the most stable, such as in a thermodynamically controlled reaction. And the answer is fairly straightforward, and the one that you need to remember is that trans the trans E alkenes are more stable than the cis alkenes. So in general, whenever you can form one, we will want, or the E alkenes will be favored thermodynamically. And stability of cycloalkenes is a little different than just for alkenes, because the ring structures are kind of constrained. If you make a double bond inside of a ring, you can't really make a trans substitution pattern there because of the bond angles that we're talking about. In fact, there's a very well-known rule in organic chemistry that unless a carbon ring has 7 or more, you can't make a trans double bond inside of a cycloalkene ring. And this is the smallest example of a trans double bond inside of a cycloalkane ring. That is trans because of the two substituents being opposite that parallel line again, trans cycloheptene. It's cyclohept because it is a ring made of 7 carbons, 1, 2, 3, 4, 5, 6, 7. And it is heptene because there is an alkene. Notice that we say trans to indicate that it is a trans alkene and not a cis alkene. We only generally do this type of naming whenever it's possible that you could have a cis or trans. We don't typically call these cis cyclohexene or cis cyclopentene because it is generally acknowledged that you can only have cis alkenes there. So the take home here is that the cycloalkenes, you need more than 7 carbons or more than 6 carbons to make a trans alkene possible. And there's another type of ring you can have, and that is the bicyclic alkenes that we were working with at the end of chapter 4, I believe. And they have a special rule that considers them, and they need even more carbons to be stable, and the rule is called Brett's rule. And Brett's rule states that if you have a trans alkene using the bicyclic bridgehead carbon, those are only possible if the largest ring has greater than 8 carbons. So what does that mean exactly? What this means is that if you have a bicyclic alkene like this, where the double bond is connected to a bridgehead carbon, such as this one, that molecule is going to be extremely unstable, because if you look at the bond between 2 and 3 here, that is basically a right angle. And that's going to be energetically very unfavorable, super high energy molecule that is going to be unstable. So what you need to have, as the rule states, is 8 carbons in the longest ring. And if you make a bicycle that has 8 carbons in the longest ring, they look really funky, first off. But you can see that just by adding in the extra carbons, we were able to make a little extra room and give ourselves some nicer looking bond angles here. You can see that the double bond is kind of twisted such that these two are in one plane, and the 2 and 3 bond angle looks a lot better because of it. So this is the basic stability rules for alkenes. Transalkenes are more stable than cis alkenes, and unless you have a big ring, you can only make cycloalkenes that are cis or Z in the old stereochemistry nomenclature we learned about. So this is 7.7, and I look forward to seeing you all virtually again soon.